Today we are going to look at double integrals in polar coordinates. And why are we doing that? And when I say double integrals in polar coordinates, I mean converting all these double integrals we have looked at, or some of them, to integrals in polar coordinates, where you're going to have r and theta in there, and cosine theta, sine theta. But why are we doing that? Because some of these integrals are going to be so much easier to integrate when they are in polar coordinates. And how would you recognize that if I don't tell you? One way you could recognize whether you should convert to polar coordinates, if the integral over the region R is a circle. Suppose R is circular or has something to do with a part of the circle, I would convert to polar coordinates. Another thing is that if somewhere within the integrand, what you have to integrate, has something with x squared plus y squared, I would use polar coordinates, because you can easily convert x squared plus y squared to something in polar coordinates. All right, so let me give you the formula for doing that. So let's recall, whenever you have rectangular coordinates and you want to convert to polar, you use the formulas x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. You need to know that. So put that down on a note sheet or somewhere, because you would need that. These are the essential formulas for polar coordinates. And here is the formula. So if I find a double integral over r, put r below here, of f of x y dA, you change the limits. And I will draw a little diagram to show you. You have alpha to beta, these are your theta limits. You have a to b, these are your r limits. And in your function f of r theta, that is, you have changed it from x and y to r and theta, and always multiply by r. Now you might be asking me, what is this r doing there? Why all of a sudden am I multiplying by r? You'll get to know that maybe in the next 2 lectures. Why? R is called a Jacobian. Just know this for now. Whenever you are changing variables in multivariable calculus or in integral calculus, you always have to multiply by the Jacobian. And in this case, in polar coordinates, your Jacobian is R. Always remember that, because students always forget to include the R. Okay?
How do you spell it?
Jacobian, let me just spell it here. So this here is a Jacobian, Jacobian, after the mathematician Jacobian. So if any of you all are looking or researching mathematicians in multivariable calculus, he's one. Okay? So let me show you a little picture to show you what I mean, where I got these from. So suppose, just look at this, and let's say it's always circular. So let's say this here is your region R. Okay? From here to here, so this first circular region has radius A. So from here to here is A, right? And then the bigger radius is B. Okay? And then, what is this alpha and beta? These are the angles. So this angle, let me put it in blue. So the angle here, this first one here, this first angle is alpha. And then the second angle here is beta. Okay? So that's where this comes from. So all I want you to remember is this. After you have changed variables to r and theta, you have found what r is, you have found what theta is, you must multiply it by r. Okay? And always remember, when we're looking at radius, radius cannot be negative, so you cannot have negative values for r on your limits, on your integral limits, okay? It's always 0 and above. Any questions? Because we're going to go straight into examples. Okay? Okay, so let's look at some examples. And there are quite a few because I want you to get the hang of them, okay? And they're quite nice. Number 1. Evaluate, of course, I suspect I didn't know how to include r when I was, I either forgot or I didn't know how to do it. The double integral over r of 1 minus the square root of x squared plus y squared dA, where r is the region bounded by the circle x squared plus y squared equals 1. Now, two things. You know, I did not tell you to convert to polar coordinates, right? But right away you should know you need to convert. Why? Because r is a circle, and look at the integrand. It contains x squared plus y squared, easily convertible to polar. All right? Okay, so let's find, the first thing we need to do is to find what your limits are. So let's see what r and your theta would be. Now, this is a unit circle. So what is the radius of that circle? 1. So therefore, r would go from 0 to 1. That's the first thing. And because we are looking at the entire circle, theta would go from 0 to, what do you think? 2 pi. Okay, because it's the entire circle. If we were looking at half the circle, it would be 2 pi. If we were looking at quarter of the circle, it would be pi over 2. Okay? All right, so we have the limits. Let's just convert. So the integral becomes, now you can, I'll put the, you can put the theta limits or the r limits. It doesn't matter what you put. So let's say 0 to 2 pi, 0 to 1. Now, let's convert the integrand. The integrand is going to be 1 minus the square root of x squared plus y squared is r squared. Remember, we did that right at the beginning. And all of this times r, your Jacobian, dr d theta. Simplify, and we're going to integrate. So the integrand now becomes 1 minus r times r dr d theta and let's simplify for some more first. R minus r squared dr d theta. Integrate now. 0 to 2 pi, then we have r squared over 2 minus r cubed over 3, and r goes from 0 to 1 d theta. Substitute 1, you get a half minus 1/3 d theta. A half minus 1/3 is 1/6 d theta. Integrate 1/6 theta from 0 to 2 pi, and then this gives me 1/6 times 2 pi, which is pi over 3. Okay. Now, just imagine, if you go back to the same question, just imagine that you were going to integrate that without converting to polar coordinates. That would have not been easy. All right? Okay. Let's go on. Another one. Number 2. Set up the double integral of 3, oh, there's no r again. Let's put the r. Now, I just told you to set up, so we're not going to integrate, okay? Just set it up. The double integral over r of 3x plus 4y squared dA in polar coordinates, where r is the region in the upper half plane bounded by the circle x squared plus y squared equals 1 and x squared plus y squared equals 4. All right? Now, just in case you want to see what r looks like, just let me show you a picture. It's not necessary for you to draw the picture, but I thought I'd show it to you. It's in the upper half plane and bounded by circles radius 1 and 4. So you have this one, and then you have that one. Okay? So this is what your r is going to be. Okay? It's in the upper half plane, so you do not need to draw the bottom. And of course, this is 1 and 2. So tell me, what are your limits for r? Anybody? 1 to 2. Right. Now, it's in the upper half plane. So what do you think the limits for theta are going to be? 0 to pi. Fantastic. Good. So I think we're ready to convert. So set up your integral. So you have the double integral. Put 0 to pi. Put 1 to 2. So convert. So 3x, what is x equal to in polar coordinates? Good. So that's 3r cosine theta. And what about y? Good. So that's 4r squared sine squared theta. What else do we need? R times r, and then put your dr d theta. That's it. We have set this up. Okay? That's number 2. Any questions so far? Okay. Shall we do number 3? So here we have to evaluate now, okay? Put in the r again. Thank you. Evaluate the double integral over r of 2xy dA, where r is the portion of the region between circles of radius 2 and 5 centered at the origin. Okay, let's set this up. First of all, oh, I forgot something. Lies in the first quadrant. That's really key. Good? Now, you can tell me what r is. What do you think? What are the limits for r? What? What is it? 2 to 5, right? And in the first quadrant, what is theta? 0 to pi over 2. Fantastic. Okay, I think we're ready to set up. So let's go. Put in your integrals. 0 to pi over 2. 2 to 5. 2xy ends up being what? Tell me. 2r squared cosine theta sine theta dr d theta. Agree? Am I missing something? The Jacobian. Fantastic. Beautiful. So let's put that as cubed. Alright? And I hope you understand why I put it as cubed, because I'm multiplying by the Jacobian r. Alright? Now, let's integrate that. So we're first integrating with respect to r. What's that? So we're integrating to r cubed, right? So that's r to the 4th divided by 4. So that's a half. Cosine theta sine theta. R goes from 2 to 5 d theta. Okay? Uh-oh, okay, we have a little calculations to do here, you know. What is 5 to the 4th? Is that 625? Check for me. I think it's 625. It is? So 625 over 2 cosine theta sine theta minus, and 2 to the 4th, that's 16 over 2. That's 8 cosine theta sine theta d theta. So when you subtract, what do you get? And you know I'm going to put this thing outside the integral, okay? It's in the way. 625 over 2 minus 8 is 609 over 2. Let's put it outside. So cosine theta sine theta d theta. Aha! We have to integrate cosine theta sine theta. I did not think we would meet a trig integral, but it's an easy one. Okay, so just let me refresh your memories. When you have to integrate anything with cosine theta sine theta like that, you need to rewrite it using the double angle formulae. Recall. Let me put this over there in blue. There is a double angle formula that has cosine theta sine theta. And do you remember it? What is sine 2 theta? That's 2 sine theta cosine theta. You remember that? So sine theta cosine theta is 1/2 sine 2 theta. So this is what we are going to use. Okay? So we're going to replace sine theta cosine theta with 1/2 sine 2 theta. So this becomes 0 to pi over 2 sine 2 theta. So the half, I'm going to multiply the 609 over 2 by the half. So that's 609 over 4 d theta. Okay? Now let's integrate. What's the integral of sine 2 theta, anybody? Minus what? Not minus 2, go again. It has to do with cosine 2 theta, but what goes in front? We just did that yesterday, spoke about that. Minus 1/2, right? You divide by the coefficient. So I'm going to put the minus 1/2, and let's just multiply this. That's 609 over 8. And 0 to pi over 2. Okay? Now let's simplify that. So that is minus 609 over 8 times cosine of pi minus cosine of 0. What is cosine of pi? Minus 1. You're right. And cosine of 0 is 1. What does this end up being? 609 over 4. So this one wasn't too bad, except when we reached that trig integral. So that is why I wanted to evaluate it, just to remind you, just in case something like that comes up, to remind you how to do that. Yes, go ahead.
Instead of using the double angle identity, could we have just done a u substitution where sine theta?
Beautiful, beautiful. I love that. Another way you could have integrated cosine theta sine theta is to use a u substitution, because the derivative of sine is cosine, right? So you could have said u equals sine theta. Beautiful. Very good. Okay? Why don't you do that one? R underneath this thing again for me, please. Okay, let's go over it. What are your limits for R? Tell me. And the limit for theta? Okay. So let's convert 0 to 2 pi, 0 to 1. Tell me what you have here. The integrand. E to the r squared. What again? What?
Can it just be e to the r squared?
Times r. If you do not put the r, it's going to be wrong, the Jacobian. Now, we want to integrate this. How do you integrate that? U substitution. Okay, so I'm going to use the U substitution here. So U equals r squared. So du is 2r dr. So r dr is du over 2. And then you can change the limits. R is 0, implies that u is 0. R is 1, implies that u is 1. So this becomes 0 to 2 pi, 0 to 1, a half e to the u du d theta. So when you integrate, this is a half e to the u, and u goes from 0 to 1 d theta. And when you work this out, you get a half e minus a half. That's when you put u equals 1 and u equals 0. Integrate further. That's a half e minus a half times theta from 0 to 2 pi. And then that is, upon substitution, a half e minus a half times 2 pi. And this works out to be e minus 1 times pi. Any questions? Okay, let's continue. We're going to do some more problems. So evaluate this integral. If I give you something like that and I don't tell you what to do, you should think that you need to convert to polar coordinates. How do I know that? Look at the integrand and also look at the limit for the integral. You see you have for the x limits, x goes from 0 to 1 minus y squared. Look at what happens. Let me just put x equals square root, of 1 minus y squared. Let's work that out. Square both sides. X squared equals 1 minus y squared. This is x squared plus y squared equals 1. So you see it's a part of a circle. So you recognize that, so you know you have to use polar coordinates. Now when it looks like that, it is not obvious what your limits are. The r limits are obvious, but not the theta. So I would advise that you draw the region. So let's draw. So as you can see, it's horizontally simple, right? So the x limits, no, let's do the y. Y limits goes from 0 to 1. So you know that right away, right? And then, let me just write that. Y limits goes from 0 to 1. And x limits goes from 0 to square root of 1 minus y squared. We have already established that this represents a part of the circle. But is it the whole circle? That's what we need to ask ourselves. X goes from 0. X equals 0 is the y-axis, right? So therefore, it's horizontally simple. So it goes from x equals 0 to the circle. So therefore, and it also tells you that y goes from 0 to 1. So you're looking at this only. So it's very essential, okay, that you draw this. Okay, now, what are the R limits? The R1. Theta is 0 to pi over 2, correct. Okay, let's change. So you have 0 to pi over 2, 0 to 1. Now 1 over this is 1 over 1 plus r squared, right? But we need to multiply by r, so put this on top. Now this integral is where you're going to use the trick. This trick. I'm going to put it in blue on the side to remind you that the integral of f prime of x over f of x dx is equal to the natural log of the absolute value of f of x plus c. Okay? So this is going to be useful here. Why? When you differentiate the denominator, let me put this integral first because we're integrating. Differentiate the denominator, what do you get? 2r, right? But you don't have 2r there. You have r. So you can use the same rule. It is ln of 1 plus r squared, but you have to have 1/2 because you do not have 2r there. Yes.
Do you have theta above that?
Where?
Do you have theta?
Oh, I forgot it. Thanks. So r goes from 0 to 1 and d theta. Okay, let's substitute. Zero to pi over 2. Put 1. You have 1/2 ln 2. And put a 0. You get ln of 1, which is 0. So you're done here. Integrate further. 1/2 natural log of 2 times theta from 0 to pi over 2. Put in the limits. You get 1/2 natural log of 2 times pi over 2, which ends up being pi over 4 natural log of 2. Okay? Any questions here?
We had like
Next,
we don't even have any.
number 2. Evaluate. Look at what we have to evaluate. So, this one is again horizontally simple. So, again, right on x goes from -1 to 0. And y goes from negative square root of 1 minus y squared to positive square. What am I doing? I have that very much backwards. That makes no sense. This is y. This is x. And from the last one, we have already established that this is a circle. Good? And as you can see, there's a 1 there, so it is a unit circle. But the important thing, is it the whole circle? Oh, it is half of the circle, but let's just see which half. What does y go from? -1 to 0. Yeah? So you already know that it's somewhere at the bottom. And then x goes from the negative side to the positive side. So we are going to do this. Okay? Good. Now, give me the limits. What are the R limits? R limits. You cannot have a negative for a radius. You don't have a negative radius. So what is R? 0 to 1. Now look at this closely. What is theta? Remember pi to 2 pi. Very good. Very good. Okay.
Could you do it from 0 to negative? No.
If you do it from, okay, that's a good question. You can also do it, he asked if you could do it from 0. I think you want to say a negative.
Yeah,
Negative,
0.
negative pi to 0.
Yeah.
Yes, you can do that. Let's set up the integral now. What do we have? Pi to 2 pi, 0 to 1. What are we integrating? Tell me. Just R? dr d theta. Now, by the way, if I have not told you before, I may have. When you have the double integral of 1, you're actually finding the area of the region. Let me put it on the side because I am not sure if I told you that before. Note the double integral of 1 dA of R is equal to the area of R. So that integral that we are finding, we are actually just finding the area of this semicircle. Okay? Okay, so let's integrate. Pi to 2 pi, R squared over 2, 0 to 1, d theta. Pi to 2 pi, 1/2 d theta. 1/2 theta, pi to 2 pi, which is pi minus pi over 2, which is pi over 2. So that's a good way to check your work. If you know that this integral, it's the double integral of 1, so you know it's actually finding the area of a semicircle, you can find the area of the semicircle. Area of a circle is pi r squared, and you just divide by 2. So it's a good way to check that our answer is correct. Questions? Okay. Let's do another one. Number 3. Evaluate again. I'm giving you enough practice with this because I want you to be able to recognize the part of a circle. So what do we have there? X goes from 0 to square root of a squared minus y squared, right? So x equals 0 to that. And then y goes from minus a to a. Let's draw. What part of the circle do you think that is? So put in the easier one. Y goes from negative a to a. So put that in. So you know it has to take all of that into consideration. But look at the x limits. The x goes from x equals 0, which is the y-axis, to this part of the circle. Where were we looking at then? The first and fourth quadrant. Very good. We're looking at this. What is R? Limits for R. 0 to a. Limits for theta. Okay, now you cannot say 3 pi over 2. You're on the right track. But you cannot say 3 pi over 2 to pi over 2 because 3 pi over 2 is bigger. So you need to have, what is the equivalent to 3 pi over 2 but is a negative? Very good. Minus pi over 2 to pi over 2. Nice work. Okay? Let's set it up. So we have the double integral minus pi over 2 to pi over 2, 0 to a. What does that integral become? R x squared plus y squared, that's r squared to the minus 3 halves. What else do we need? R dr d theta. Now let's simplify that before we integrate. That's r to the negative 3 times r, which is r to the negative 2 dr d theta. Let's integrate. Put your outermost integral, leave it alone. Integrate r to the negative 2. What's that? Negative r to the negative 1, right? So let's put it as negative 1 over r. And r goes from 0 to a, d theta. Now you know something is wrong here. You know why? What's wrong? R is 0. Okay, so we'll stop here. So we'll just set it up. Okay, something like that we'll have to take limits and so on. So let's leave it alone. So let's just set up this integral. So let's erase this part here. And I'll just say set up. Set up but do not evaluate. Okay. Okay. I want to give you one, but I want to do number 4 first because it's a tricky one. Very tricky. Very, very tricky. Now, I want you to do this. Now, I'm just going to say set up. We're not going to evaluate it, okay? So set up, but do not evaluate this integral. And I want you to use polar coordinates. I want you to do it. So you must be saying, what? There's nothing there that's circular, right? But I want to show you that you can actually set up any integral using polar coordinates. So I want to do this one. It's a real tricky one, okay? So what I want us to do first of all is to draw the region. Good? So let's see what we have. We have y going from minus x to y equals x. And we have x going from 0 to x equals square root 6, okay? And it's vertically simple. So let's draw. We want to draw y equals x. Let's put this in here. And y equals negative x. Okay? This is our 0. And we want to put in the line x equals square root 6. So let's just say that this line here is x equals square root 6. So the region that we are actually looking at is this region. All right? Which has nothing circular about it. But we can still do it. It's tricky. The first, I think the easiest thing we can find what theta is. Okay? So, what are the angles for theta? We're going from here, this, to there. So we're going in this direction. Let me show you. We go in here. All right, so we want to know what this angle represents. What is this angle and what is this angle? Negative pi over 4 to pi over 4. Excellent. Beautiful. Now we want what r is, right? Now we're starting at the origin here, so r would start from 0, but to what? Now use the fact that x equals square root 6. That is what we need to convert to polar. Good? But in polar coordinates, what is x? X is r cosine theta, right? So from this, r is square root 6 over cosine theta. And so r goes from 0 to square root 6 over cosine theta. And so the integral is the integral from negative pi over 4 to pi over 4, 0 to square root 6 over cosine theta. And is it just a double integral of 1? So we just need r dr d theta. Okay?
So we know to use pi over 4 because it's like a unit circle and that's the 45 degree.
Why did we say that again?
Because it's like that, like a unit circle and it'd be pi over 4 is 45 degrees.
No, I'm not understanding your question. Say it again.
We know to use pi over 4 because that's a 45 degree.
That's a 45 degree angle. The line y equals x and y equals negative x makes a 45 degree angle with the y-axis. Okay, so that is why we are using pi over 4. So that one was a tricky one, okay? Any questions? Okay, this next one, I just want you to set it up. Don't evaluate, just set up. So I'm going to say set up, but do not evaluate. Okay, let's draw. What are we looking at here? What region? So it's a semicircle, right? Okay, great job. Radius 3. Okay. So r goes from 0 to 3. What about theta? 0 to what? Pi. Okay. Give me the setup, anybody, please. Sin r cubed, are you sure? R squared, and times r. You don't multiply the r squared by r, it's the entire function. Now I only asked you to set up, but what if you had to integrate that? Well, how would you do that? Anybody? Substitution. What is your u? R squared. Very good. And it's going to end up being a half. When you use substitution, it would be a half sine r squared. Okay? Any questions? Let's move on. All right, so let's look at some volume here. Good? Example. Find the volume under the circular paraboloid z equals 12 minus 3x squared minus 3y squared and above the xy plane. Okay? All right. So this is what you're going to integrate, this z function. Remember, you're always integrating the double integral of the z function, which is your f of xy. Good? Now you see how the z function looks? Use polar coordinates because you see an x squared plus y squared in there. So that should be your first thing you need to do. Where's my pen? Let's do that. So let's say, so z equals 12 minus 3x squared minus 3y squared. Recognize that this is 12 minus 3 times x squared plus y squared. and this is equal to 12 minus 3r squared. Okay, this is what you're doing. Any questions? Okay, now we need to know the limits for r. This is what we are integrating, but we need the limits for r and we need the limits for theta. It is above the xy plane, so what we need to do is to intersect this with the plane z equals 0. So put 12 minus 3r squared equal to 0, and that will give you your limits for r. Okay? All right, so limits for r. So 12 minus 3r squared is 0. Let's solve. 3r squared is 12. R squared is 4. So r is 2. Remember, we do not want any negatives, okay? And what do you think theta is? It's very obvious. Theta can just be one thing. What is it? It's the entire circular. Look at the question. Under the circular paraboloid. So they didn't tell you part of the paraboloid. The entire circular. So what is it? 0 to 2 pi. Okay, let's set up now. The integral, so volume is equal to 0 to 2 pi, 0 to 2, 12 minus 3r squared times r dr d theta. Integrate. 0 to 2 pi. I think we need to simplify this first, okay? So distribute 12r minus 3r cubed dr d theta. Integrate now. 0 to 2 pi. This is 6r squared minus 3/4 r to the 4th from 0 to 2 d theta. When you substitute 2, you end up with 12. 0 to 2 pi, 12 d theta. Integrate 12 theta, 0 to 2 pi, and that is 24 pi. Okay. Next question. Another volume. Find the volume of the region that lies inside z equals x squared plus y squared and below the plane z equals 16. If you had to draw this on your calculator, and you can do that at home, it's going to look like a little bowl. Okay, let me show you what it's going to look like. I'm doing, this is not good, Delia. We're in 3D, right? Let's go back. All right. I'm not going to talk about my drawing, so let's just do it. I'm tired of talking about it. Okay. So it's something like that. So this is your z equals x squared plus y squared, and below the plane z equals 16. So something like that. This is something like that's going to look like. So that's what you have to find the volume of. All right. So let's convert to polar coordinates because we see this x squared plus y squared there. Okay. So z equals x squared plus y squared gives me that z equals r squared. Okay? We need to find the limits for r. To do that, we need the intersection between the two planes. That is going to give you a radius. All right? So solve z equals r squared. and z equals 16, we have that r squared is 16, so r is 4. So the limits for r goes from 0 to 4. What about theta? Again, this is obvious. 0 to 2 pi. Good. Okay? So volume is going to be the integral from 0 to 2 pi, the integral from 0 to 4. Now of what? Now careful, don't do the Jacobian thing yet. We are below a plane, right? And inside this cylinder. Good? So we need to subtract the two. There are two z's, right? So it's below the z minus 16, and the z equals r squared. So it would be 16 minus r squared. Now you need to multiply by your r. Okay? Now I think this let's do it. We can simplify that. It's not too bad. 0 to 2 pi, 0 to 4, distribute 16r minus r cubed dr d theta. Okay, integrate 0 to 2 pi. This is 8r squared minus r to the 4th over 4 from 0 to 4 d theta. Okay, you need to help me here. 4 squared is 16. 16 by 8 is what? 128. Thank you. And what is 4 to the 4th over 4 is 4 cubed, which is 64. D theta. That's the integral from 0 to 2 pi of 64 d theta, which is 64 theta from 0 to 2 pi, which ends up being 128 pi. Any questions so far? Find the volume of the region that lies under the sphere. X squared plus y squared plus z squared equals 9. Above the plane, z equals 0. And inside the cylinder, x squared plus y squared equals 5. Okay? Do I want to draw this for you?
Yes, please.
No, I don't want to draw this. I know you want me to draw it, Phil, but I really don't want to do that. Okay, first of all, we need to decide what we're going to integrate. The z function is always what you want to integrate. Remember that, okay? So you need to take the sphere and solve for z. Right? So take x squared plus y squared plus z squared equals 9. And you know what I would do even before I start solving? I would convert to polar coordinates right away, because I can replace this x squared plus y squared with r squared. Makes it a lot easier, okay? So r squared plus z squared equals 9. Z squared is 9 minus r squared. So z is the square root of 9 minus r squared. We are only looking at the positive square root because it's above the plane z equals 0. Okay? That is why we did not take the negative into consideration. Good? Now, how do you find your r and your theta limits? You continue the rest of the question. We have done under the sphere and above the plane. Now, inside the cylinder, x squared plus y squared equals 5. This is going to give you your r limits. Okay? So this says that r squared is 5, so r is square root 5. set it up. Okay, so give me your R limits, please. 0 to square root 5. And give me your theta limits, please. 0 to 2 pi as usual. 0 to 2 pi. 0 to square root 5. Can you give me the integrand, please? Times R. Okay, we're only setting up this one. But tell me, if you had to integrate this, how would you do it? U substitution. What is U? I would put 9 minus R squared for you. Okay, so let me just put on top, set up the integral only. Okay. And I left the best for last. Saving the best for last. And why? Because this one is challenging. Okay? So let's do this. Find the volume of the solid under the surface z equals x squared plus y squared above the xy plane and inside the cylinder x squared plus y squared equals 2y. Isn't that beautiful? Okay. You really want me to draw? Are you teasing me? Are you kidding? Okay. I wouldn't be surprised if some of you draw this for me on your assignments because I've seen this before. Yeah, that's really nice to see. Now, look at this question. The volume under the surface. So, it's under the surface z equals x squared plus y squared. So, remember when we first defined volume using double integrals, the surface that it's under is what you're integrating. Good? So really, we need to find, and I'm doing this because we have a lot of stuff to do there. We need to find the double integral over r, and we'll do the r in a little while, of x squared plus y squared dA. That's what we want to do. Okay? And what is this r? Inside the cylinder. X squared plus y squared equals 2y. This is what we're going to use to convert. Alright? We need to find our r and theta from this cylinder thing. This is not the normal cylinder that we normally have. This is a little more challenging. Okay. So what I would do is to convert to polar right away. It will be easier to solve. Okay? So this is r squared equals 2y, which is r sine theta. Good? Now we need to solve. So r squared minus 2r sine theta is 0. So r minus 2 sine theta in parentheses. So r is 0 or 2 sine theta. So these are our limits for r. Good? R goes from 0 to 2 sine theta. Now, this is where I want you to be so careful. What are your... Now, by the way, before I ask you what are your theta limits, r equals 2 sine theta is a circle. Go back to Calc 2. This is a circle, right? Anything of the form a sine theta where a is a constant or a cosine theta is a circle, okay? What are the limits for theta? For this circle? Right, so you assume it's 0 to 2 pi, right? But 0 to 2 pi goes around the circle twice. It's actually 0 to pi. That is why I'm doing this. So this is not an obvious one. And let's just see why. Let me just draw up the coordinates for this. Circle. Theta and r. So let me put 0, pi over 2, and pi. Let me show you. When theta is 0, r is 0. When theta is pi over 2, r is 2. When theta is pi, r is minus 2. What am I saying? What am I doing? I'm getting tired. When theta is pi, r is 0. Good? This is what this circle looks like. You start here, pi over 2 is 2, and you go back here. So this is it. You complete the circle. You have already formed the circle between 0 and pi. So be very careful when you see a question where you have r as some constant times sine or some constant times cosine. Do not assume that r goes from 0 to 2 pi. Okay? So that is why I wanted to do that for you. Good. Let's set up the integral now. So volume is equal to 0 to pi, 0 to 2 sine theta. What are we integrating again? X squared plus y squared, which is what? R squared times r. dr d theta. Now I want to complete that because I want to show you something, just in case you get something like that for homework, what to do. 0 to pi, 0 to 2 sine theta, r cubed, dr d theta, 0 to pi, r to the 4th over 4, 0 to 2 sine theta, d theta. Okay, which is 0 to pi. Now, when you put 2 sine theta for r there and you divide by 4, you are going to get sine to the 4th theta d theta. Now, look at that. You see, if you have something like that in your homework, this is quite wicked to do this. It's going to be quite long. You did that in Calc 2. Quite long. So I would advise you, or I would let you to just put that into your calculator. Okay? So just use your calculator. When it is so intricate, just use your calculator and you'll get 3 pi over 2. So from calculator. Okay? Any questions?